So it's basically everything leading up to quantum machine learning. There was a lot with quantum algorithms, quantum-inspired algorithms that had transpired, and it's good to know about, and especially the more recent quantum-inspired machine learning literature as well. And this is for running on GPUs and CPUs. So this is discussion 119. My name is Kevin Kotchak. I'm the founder CEO of Chemical Q Device. This is Thursday, January 25th. And this is for effective QML algorithm implementations for medical R&D. So what I did here is basically there's a big paper, big survey in QML, or quantum inspired machine learning, as of last year that really pulled a lot of things together. I highly recommend it. I think they're Australian and some Chinese researchers with that too. And what I basically did here is laid out, so this goes back all the way to 1995, these kind of like the people that got this started, just wondering, could you use quantum mechanics, which is the basis of qubits and then the quantum computation that we have today, could you use that for algorithms? So the first paper, of course, is not going to touch everything. But at that same time, it laid the foundation for the QML that we see today, like the penny lane and the Qiskit and all this type of stuff that you can do. So going from there, it was Han and Kim. They started to do these parallel quantum genetic algorithms, and that was the thing, is genetic algorithms to begin with. And same thing with myself, as I found, basically 20% increase in loss efficiency running a circuit in parallel, two circuits in parallel as opposed to a single one. So you'll see that in at least one other case here, using parallel circuits instead of just one. It's basically more processing and machine learning towards the algorithm instead of the overall process of machine learning with optimizer, loss function, giving it more algorithm, per mini batch or epoch. So in 2002, you see Han and Kim again. So this is a quantum evolutionary algorithm. And then this, it's a particle swarm optimization algorithm. They will see a lot in literature. And then also in 2007, this quantum ant colony algorithm. And again, with Sama et al. In 2007 as well. Now in 2011, continuing this QEA research. So this is way before the time of, penny lane, Qiskit, using quantum mechanics for, machine learning purposes. And 2011, same thing with Nicolau too there. And then by 2012, there's actually a survey to pull all this together. So, now we're talking about heuristics and meta heuristics and these types of things, being considered for quantum. And then in 2017, another quantum ant colony algorithm there too. And then also, going into 2020 is when you hear this term, quantum-inspired meta-heuristics. And what does that mean? I'll go over it a little bit, but it's basically, it's a different approach to different types of different approach than other types of conventional algorithms, and this is with quantum mechanics now, to try to get an algorithm that's more suited to different use cases, but in a more abstract way of going about things, like a qubit, a quantum bit. And then, so this continues. So quantum-inspired meta-heuristics in 2021. And then, so you see in 2022, combinatorial optimization problems. And then at this point, there's a fair number of these quantum algorithms, okay, to be considered. This is a very legitimate field to do QML. So it's just quantum algorithms, basically. And all of these are run on CPUs or GPUs. So you can't do this. These are easier, but the literature beforehand, especially no QPUs. And then you'll see more meta heuristics with it too. And then you'll see another quantum ant colony optimization. So going into that, you'll see, so this is basically the Moore Narayanan. So these are some of the kind of the founders of quantum inspired algorithms. And, on the previous slide, there's these, and I'll get to some of the other, more common names that you'll come across. So these were, from University of Exeter, and basically saying a novel computational paradigm, which is inspired by the principles of quantum mechanics and quantum computing. Okay, so this is the one that says, you can do this. This diagram is a double slit experiment, which is synonymous with quantum mechanics if you took physics before. And then so they went on to these quantum inspired genetic algorithms. So again, this is following the timeline from the previous slide, and used to inform and let's see, inspire more efficient evolutionary computing methods. So a lot of these, if you're strong in algorithms, traditional algorithms, a lot of this will ring true. And it's basically now you're doing it with some form of quantum computing, quantum mechanics, qubits, gates, and you don't necessarily have to use, say, for instance, superpositioning in one case and another. You don't. It's just based on the research and what you're trying to accomplish. And basically what they say is quantum inspired genetic algorithm performs better than the classical counterpart for a small domain. And you'll see in these where I underline is basically every time the quantum inspired method produced better results. Okay, so this graph here, and there's new people coming in. This graph here, basically these quantum evolutionary algorithms, they're the top three. Okay, and then what they do is they actually normalize this. So you'll have these top three compared to the CGA. And I just did a rough calculation of its profit versus generation. So it's, approximately 15% increase in profit with the best QAA algorithm versus, the standard, CGA genetic algorithm there. And, so this is where, you would have to have some type of foundational understanding of quantum circuits and quantum gates and these types of things. But they say it's a qubit chromosome. And, basically it's done in a different type of fashion, right? Quantum mechanically. And this is all, the basis unit for this is, I believe, I don't know if it's all the time, but it's typically the quantum bit instead of having classical bits. Now, the quantum bit is made up of classical bits, but traditionally that's typically what you use as the qubit quantum bit as the basis. And, so they said for this knapsack problem, they got better rapid convergence, good global search capability, best other genetic algorithms. And then in 2001, remember from the timeline, the parallel quantum inspired genetic algorithms are superior to just standard QGAs, as well as other conventional genetic algorithms. So you can use, in these days, you can use torch.neural network, or it's torch.nn.module to do parallel algorithms or whatever. Same thing, there's an equivalent for TensorFlow too. And then in 2002, you'll see the QEAs for combinatorial optimization. And, here's where it is. It's defining at that time, they call it Q dash bit instead of QUBIT, and then Q gates too. So these things are just, you're going to be using quantum gates, but at that time, these are kind of like the things that are developing, to get better results using quantum mechanics. So this top one here is basically, you'll see, so what you're looking at here is these optimal values. So they said for a standard quantum evolutionary algorithm versus a classical DB, some particle swarm optimization algorithm, and then this quantum ant colony, it's 100% R opt for all of these. And you see the 0, 0, 0. So it's not just one paper, it's many papers that, they're claiming that they're getting benefit by doing, quantum inspired algorithms on just traditional classical hardware. And, so this is another one here. So particle swarm experiments results show much advantage of this quantum specific particle swarm optimization algorithm compared to the traditional one. And you'll see, so this is another ant colony in 2007. And the one that's very interesting, because you'll hear about the physical approach with quantum annealing, an actual quantum annealing, is there's actually, a quantum annealing simulators that you can use today. And what they found is basically with the quantum algorithm, it's 1 over square root of delta, which is better than 1 over delta operations. So that's an advantage. And we start talking about these things like quadratic advantage, exponential advantage. In the supplementary, I'll show you where exactly things are in a number of these algorithms. So yeah, they say for this condition, the quantum simulated annealing with quantum, mechanics inside this CPU or GPU is performing better. Okay, so here's another one as far as charts. So they went a little bit further with this. So this is a Zhang in 2011. And so basically, they're all of these variants of quantum inspired evolutional algorithms. So you see the bulk of it is QIEA, and then there are different variants based on that. So you'll see Q gates, so it wasn't always the case, we're using RY, RX, RZ, C knots, those types of things. These things appear to just be, still forming at that time. And they said, so it's approximately 11% increase in the best. So this black one with this specific BQIEA with crossover and mutation operators versus the classical variant, which is the CGA, which is this bottom one. So basically they did this to improve they said fewer no convincing comparisons between of these evolutionary algorithms with optimization, like traditional ones, particle swarm, ant colony, so on and so forth. Okay, so this next one is very interesting because the use case is so cool. It's a nuclear reactor. So it's a quantum evolutionary algorithm that optimizes the pressurized water reactor of this nuclear power plant. So what to focus on here is the CB, which is the boron concentration. Higher is better. Okay, so you'll see their work down at the bottom here. So they said, it's the highest for their current quantum algorithm. And then they report this average, which is also higher by a little bit over a different work. And, this is still going back a little way to 2011. The standard deviation, which was actually quite better than the other competing work, is this De Silva, which is QPBIL, going back to 2010. So anyways, the cool and interesting thing is this has left the minds of, us researchers, and this is like, trying out the algorithms and it's basically to, it says the probabilistic representation and possesses fast convergence to the best solution utilizing the phenomenon of quantum interference. So quantum interference is experience between different qubits. And, so the other two are superpositioning and entangling. So that's what they're basically saying is, the way that these classical computers are programmed, with quantum information or the quantum mechanics is that it just, that's what they said. It was the quantum interference in specific that helped. And they say it's very efficient for solving the present problem, with a smaller number of valuations than its classical optimization genetic algorithm, this other meta heuristic that it's going up against. Okay, so here's the other one. So this is artificial intelligence review for the top one. And this is one of those, it's out there if you need it, exhaustive surveys. Some of these are behind paywalls. The IEEEs, and if you don't have an IEEE, it would probably be recommended to get that for this type of research. The algorithms, the same thing with traditional algorithms as well. So this other one, the application of quantum-inspired ant colony algorithm with automatic segmentation of a tomato image. It's basically, when you see these things like auto QML or automatic segmentation, it means the technology's improving. And you always want to compare this against, traditional algorithms, right? So where is that compared to this? How can we, insert there if it's just a non-machine learning algorithm, that's proven that it makes sense to use it. It's just more of an expertise thing. You have to know something about quantum bits and gates and these types of things. And they found that the quantization, which means, basically it's an ant colony algorithm that uses quantum mechanics, has a better diversity of population, overcomes, the rest of these, premature stagnation phenomenon effectively. In addition, segmentation speed and precision has improved, and it says greatly in the specific one. So you kind of take all of these and then, short of, reading every single paper and going through all of them, you kind of think like, okay, so there's a number of authors that have have proved, some benefit of using quantum mechanics. And then, oh yeah, by the way, it spawned a field called quantum machine learning. So I think where that puts us, okay. So there's a couple, are there any questions at this point? So I know we probably get a diverse background as far as people coming from quantum computing and others in classical that may not have gotten into, say, quantum meta heuristics.
Uh,
So feel free
uh,
to, yeah, go ahead.
so I came a bit late. Did I miss anything major or?
Yeah, so I'll have the slides up too. So basically,
Uh,
it's tracking the progress of first thinking that we could use quantum mechanics in algorithms to getting results. And then now I'll be getting into more of the meta heuristics of it all.
okay, so I just wanted to comment. I also did a paper on this. I don't know if you saw that on my account. I did a paper on deep quantum neural networks and how it actually speeds up classical inference.
Yeah, yeah. And what year was it?
Yeah, so I'm saying I also had some work on this. Wanted to mention that too if you wanted to look it up.
Okay. Yeah, I appreciate that. So what brings us to the next part here is basically, okay, so we start to get into meta heuristics. So it's something that you may or may not have studied, in school, or if you got into data science later in life. It's one of those things that, so here's 4 good points with it. And because the quantum part is all into this, or it's part of it. A meta heuristic is a procedure that allows finding good solutions to a difficult optimization problem. Okay, pretty useful. It makes few assumptions about optimization problem and are useful for a variety of problems. So that's a key. And they're more abstract than simple heuristics and can use low-level heuristics or search algorithms. And compared to other methods, a meta-heuristic actually does not guarantee to find the optimal global solution of a problem. So they're more abstract, and as opposed to going straight at something where, yeah, I'm assuming you would get in a certain landscape that you can't get out of classically. But you'll hear this word, meta heuristics is a good goal for using quantum algorithms. And in case you joined late, we're still in the portion of quantum algorithms. So in 2021, you'll see this using genetic algorithms, and this was actually for coronavirus analysis. So, starting back in 95, when it's just being thought of, we can use, quantum mechanics, with a specific algorithm. And now it's up to the point of using it for, COVID analysis with these specific, quantum algorithms. Now, this next paper has really good figures. So this Meduna paper, quantum algorithms for combinatorial optimization problems. And here, 2022, starting in 1995, here's a survey, which is good to see. So people are putting together this work. It's always a good sign to see these types of reviews. And, so basically in the left, they show quantum evolutionary algorithm, 29%, quantum particle swarm. And they say this is related to number of applications per algorithm branch. Variational quantum algorithms, 17.9%. So you see a bunch of the other ones, including Grover's too. And this middle graphic is interesting because it says it starts with David Deutsch, Deutsch algorithm, and then it splits off in between these, and you'll see Grover's in the middle, and then some of these other ones. So the most I've talked about is this QEA and also quantum particle swarm, but it kind of gives you an idea of what's all out there. And I've mentioned the knapsack problem, and as far as like the types of things that's done for these combinatorial optimization problems with quantum graph problems, you'll see different things here. So a good paper for good images, and so is this paper in specific as well. So you'll hear a lot about using it for classification, and here you go, like clustering, high dimensional problems. And this is still talking just about quantum-based meta heuristics, the algorithms, the small algorithms. And then the different methods is quite surprising. I mean, to me, because this is obviously a field that a lot of people research, and just look at how many, if there's probably 24, something like that, of these different quantum computing meta heuristics is what they call. And then I'll be transitioning next into quantum machine learning, which is this light green, and the different efforts that have been made with that too. Okay, so lots of people saying good things about quantum. Basically, it's used more than any other strategy for accelerating convergence, enhancing exploration and exploitation, significantly influencing metaheuristic algorithms performance for that one. Now, this one, I think, takes us to the end of just the algorithm portion. So this is DOS. So this is DOS et al. And this is another quantum ant colony optimization. What we see here is basically, 4-dimensional traveling salesmen. So that's basically, you have economy and environmental, so what you would use the most money, and then what has the biggest impact on a salesperson going to these different job sites. So it gets a little bit more advanced, right? You're not going to see a basic, quantum inspired ant colony optimization at this point. And this is 2023. So this leads us up to quantum machine learning. Are there any other questions from anybody?
I just have more of a comment. Some of the work that I did also for quantum optimization in particular, I think I also made a quantized A-star genetic algorithm and different algorithms. And I wanted to say that, especially for quantum, I think the main sort of implications is, of course, the more qubits you have, the more you'll be able to solve larger scale problems. And also when you, assuming the error correction gets good enough, the main sort of implication will be if we have like a few million qubits, we'll be able to do a lot of more useful things. Yeah.
Yeah, I appreciate all that. And, it's all important. So let's see here. So this is a perfect segue here. So this is getting into quantum machine learning. Now, if you're not familiar, these terms, deep learning typically refers to 3 layers of, a traditional, sets of layers in that. So quantum deep learning is a little bit different because now we have gates, and say a gate might not have as many as different separate operations, but, the qubit obviously has more information. So you'll see this in this, and you see GAMS in 2006 and then NVIDIC. And I actually took a course on this several months ago, kind of where I started my serious QML journey. And he actually, he passed away in a hiking accident. And before all that, he made a really good, it's up on YouTube right now. It used to be on edX, and it's a quantum machine learning instruction. So it's with him, and I think the other gentleman is Matter, like the Matter Lab up in, I think he's in Toronto too. It's also got Seth Lloyd, Maria Schuld, and they're not together, but they're filmed separately. And I recommend it to anybody. Go on YouTube, and there's like 41 of these. So each might be, I don't know, between 5 and 10 minutes. As far as the clips. So he was foundational in QML, and how many people, kind of think of like what QML will be like in the future there too. And, so going from there, so in 2020, and this is kind of getting the wheel started for, quantum machine learning, quantum, deep learning too. So you see Garg et al. And then going into quantum matter, and you'll see QML classifiers, so classification. And you still see this in 2021, still introductions to QML, what is it defining, these types of things. Now, the 2 papers I would really recommend to see is basically they're Los Alamos National Laboratory papers, Cerezo and Hussein. The first one is Challenges and Opportunities of Quantum Machine Learning. And the second one is, in specific, this is trainability issues with quantum machine learning. So, it's stuff that you have to know. And it could be anything from, global measurement is not good for barren plateaus. And we know that, high qubit counts can definitely help, or I'm sorry, hurt, minimums too, or, induce barren plateaus. And then from there, you see some other things. So the QML trainability is the one actually, Thanaslip and Cerazer are the two papers I've read, at least once each. And then, you see some of these other ones getting more into application with pharmaceutical speed. Tensor networks. So tensor networks, a lot of people have high hopes for. This is basically like get the qubit count up. However, it's not an exact solution like state vector algorithms are. So that's the downfall with that. And you'll see. So a lot of these papers I got from this Hoyne et al., which is a 2023 Kimmel survey. It'll say something like quantum inspired machine learning, a survey. And it's an awesome job, and I'll get to more of the figures related with it too. And you'll see, so when it starts to mention auto QML, it means something with QML is working, right? So this is good to see. Like the other gentleman that came on, he's reporting, that he's getting results there too. And the other one I came across too is actually, I don't think the author, I have to fix the author name, but it's a quantum machine learning for healthcare for this bottom right one as well. So you see from approximately 2006 all the way up through 2024, which makes sense. And a lot of people want it. We want to do machine learning with some type of quantum mechanics, and it's more involved than say just a single quantum algorithm. So, and hence Penny Lane especially working on a lot of these issues to make it accessible to us. And so basically this is the intro slide, and where we are here is we're going down to QML. So this third point, I'll have all the slides up. I think there was a question too, the YouTube about the QML Tanmoy. So we'll talk about that. You just have to search for quantum machine learning, like Peter Wittig. It's WITTIG, something like that. Or yeah, you'll be able to find it pretty easily. It's a huge series. So and what was mentioned before earlier is do we need hardware? When will it be available? These types of things. Now on the software side is we have these tools, and these tools are being applied not only to QPUs, but the same thing for this Penny Lane software that they've used on the Perlmutter supercomputer, circuit cutting. So you can cut to a certain degree qubits, and then perform these operations and then get the end results later. Mid-circuit measurements and qubit reuse. And I think actually Honeywell or Quantinium was big behind that, but it'll be big for quantum inspired machine learning too. Tensor networks, I don't think any QPU will be able to run anything like that in the next at least 5 years. Parallel and neural networks. So these are continuously updating workflows. And you need to have basically devices that are practical. They're not super expensive. They're available, no noise, these types of things. Anything like that is not good for quantum machine learning. So on the other side too is basically with GPUs, and there's been articles, going from, Tom's Hardware. It was a ACM, which is computer machinery paper too. It says a single GPU will outpace, any quantum computer for some time. Now, the good point with that is basically in a couple months here, second quarter of this year, the H200s, which have approximately 1.4 times the bandwidth of an H100, and then actually 76% more RAM. So if we were stuck, and I still use my max as a 51 gig, high RAM CPU. Now, some researchers, you'll use A100 40 gigs, and I can use that one too. Some will use an 80 gigs. So it's basically going up from 80 gigs to 141, and that's 76% additional RAM to help with quantum computations. So that's a kind of a flagship GPU, but these are trends I think that even if you're not using an H200, if you're not like in industry, using a lot of them, you'll see these trends, more bandwidth and more RAM. So this is the basic Wittig here, and this is how you spell it to put it into YouTube. And this is something when I came across this, it didn't really, I was like, okay, so what? But I now understand. So lost landscapes can be like egg crate cartons, like on a mattress, and you can get stuck in these wells. And what quantum tunneling allows you to do, and this is more on the one on the right one, is basically to access this classical, this is not accessible with traditional classical methods. So this is tunneling on the right side, is that, using, quantum mechanics and waves, that it's actually going through, this lost landscape. And this is the end goal, right? You're reporting a loss, and that corresponds to an accuracy. So if your loss is not low, it means that you haven't reached the global maximum. I mean, you could have other global minimum. You could have other local minimums that you can get stuck in, but ultimately, I think just going back over this again, it's like, it's a huge upside. Basically, if you can use it predictably to get to the lowest loss and say, cut down on other different traditional mechanisms that you'd use with, like coarse things like changing the learning rate, these types of things. And yeah, so University of Toronto is behind a lot of this. So this is basically, and there's, I'll have this up, and this is basically for you. So this is Garg et al. Did this advances in quantum deep learning, an overview, and different projects are at different stages here. So some of them say, like the last one says with Henderson, which is a big name too, quantum sampling based approach, generative training, much faster than Gibbs sampling. Okay. So, it's worth going through these, and these all, this is basically to point back to the original paper. And same thing with this. And you'll see, say, for instance, with Zhang et al. So these are 2020 or before, improved variant of the quantum language model. So figure like NLP stuff, or, large language, which has higher representation capacity. So we're talking about machine learning, deep learning. That's typically the area that we start getting into, semantics, semantic search, these types of things. And you'll even see with this last one, hybrid workflow toolkit for NLPs. Now, I also wanted to clarify one thing, is that you could use PennyLane on a small laptop with quantum algorithms and classical algorithms. However, if you have a huge data set, or if you have huge, algorithms, or if they're part of other deep learning, neural networks, then it quickly bogs down. And if you want to use more qubits, and I get up to say like 20, you really start to see that. And so that's one approach. Now, another approach is to have dedicated quantum simulators. So this is like the lightning.gpu or lightning.cocos, and you can actually do all of that quantum processing on that simulator in the cloud somewhere. While, say, for instance, the rest of your, workflow is being done on, a separate GPU that processes some other traditional algorithms. So, basically this is, you'll hear this over and over. It says this 2020, the outlook for future developments in areas at the intersection between machine learning and quantum many body physics, and that's what that covers on that specific one. So if you're coming from machine learning and you're kind of curious of what is going on, and you don't know what quantum circuits are, because I kind of am familiar with different representations of this. So on the left is basically traditional machine learning. So you're going to have some aspect of pre-processing images, stretch, horizontal, vertical, these types of things. And then you're going to do training, and then with your validation set separately, to get a prediction model. So what's added with the quantum circuits is basically the encoding. So you have classical data, but that has to be turned into quantum states. So this is something what like a PennyLane angle embedding template does, is it turns it into quantum states in your classical computer. And you'll see all these similar steps, but at the end, those quantum states, all this here is showing it's in quantum states somehow. And decoding goes back into classical, and then that's their prediction model. So you'll see there's a cost associated with these. So you have to be aware of designing circuits, because if you're losing, if the benefit, like the speed up of the quantum algorithm is not as great as your it does not overcome the encoding and decoding. And I think especially the encoding part uses more RAM. So those are things to be aware of. So basically, this paper, is a good overview too. So it says classification with quantum machine learning, a survey. So 2020, and it's good to see, because it's a complex topic, right? Machine learning to quantum machine learning, and now we're seeing a survey. It was at 4 years ago, so it's a good thing to see too. And this kind of finishes up for 2020. So you'll see different types of, so the algorithm achieved higher accuracy in many medical data sets than the classical counterpart. So this is, the number of times we've seen this is already like 6 or 7. And it says also here's another parallel computing, and I've done a lot with this too, or more so on the software side, for image classification for improved efficiency and classification performance. So there's all of this, potential benefit out there. And what it'll come down to is the people that can use it effectively, right? So some people are going to have to know how to use, quantum algorithms, and, some people are going to have to know everything, right? You're going to know machine learning, deep learning, quantum algorithms, the whole thing. So here's another one, this Chen et al. They said they used quantum K nearest neighbors with superpositioning for speed up. And then you'll see the Seguir et al. Accomplish higher accuracy with less complexity, less time complexity comparable to other traditional algorithms. So again, it's typically in the abstracts or conclusions. Sometimes I get it out of the figures here too. And this is one of the papers, or these above figures actually come from the Cerezo et al. And this is one you should read. And it's a little bit confusing unless you know everything like 100% when they're talking about quantum hardware or when they're talking about, quantum inspired. And they mention both in the paper. I think they more so are hinting at using it for quantum hardware. But say, for instance, tensor networks, it's going to be very challenging to use that on quantum hardware anytime, for many years. Okay, so these are 22s, and then the 23 is the other one to check out. That's another Lano paper, and it'll say like, these are some of the issues, lots with barren plateaus, which is like, unfavorable loss landscapes. Like when this ball, you don't want it to have like a steep cliff. You want it to, have a certain appearance with it. And, there's this Zagundry paper as well, a review and case studies. And, so this is additional information. Now they kind of broke it down because like the example that I gave with Penny Lane on a laptop with classical quantum algorithms, totally doable. This is coming, from their discussion forum. And in all these things, you're still going to have some classical algorithms, right? So whether it's the loss function, if it's the optimizer itself, it's going to be a mix, right? So the term hybrid classical quantum machine learning can mean two different things, so it could mean that you're using, QPU with, a CPU, and the QPU runs the quantum algorithm and the CPU runs, the classical algorithms. And it can also mean that you're using both classical and quantum algorithms on classical processing, which has, been the case, and it'll be the case for, some time. And they'd introduced this Q-sample encoding, which is a hybrid of amplitude and basis encoding. So it's good to see new innovation. And it's also good to see the reviews saying like, okay, this is the generalized, this is our understanding of this field with QML. And these are more papers too. And this one in specific, this Kapoor one, we demonstrate 10 to 100x speedups and end-to-end drug discovery pipelines in our QML learning. So that's worth checking out. And there's just other different, applications and surveys. And I think it's pretty safe to say between the quantum algorithms and the QML that this is pretty well being covered, right? As far as like, if you have a small startup, I wouldn't recommend getting into a field that, isn't moving, developing at a fast rate too. Any questions?
Yeah. So what are the main future directions and challenges, especially for implementing QML, when it comes to like number of qubits and coherence time and reducing error rates in the actual quantum computing hardware?
Yeah, so for QPUs, and this discussion comes up all the time, is basically everything that's been done to this point, and especially like when you do machine learning, you're talking about, if you have mini batches, 10 mini batches per epoch, that's running the quantum algorithm that many times before you even get, that the value for that epoch. So what it looks like, and I don't know for medical, because if you mix in anything with decoherence, latency, not as much, but noise, quantum noise, these types of things in patient data at any point of the pipeline, I think it's going to be a hard sell. But I think in certain industries, it's going to feed in, right? So I saw some of these studies where you have some, application with, quantum hardware to fix an algorithm in a machine learning thing, but it's not necessarily being constantly updated. And again, going back to cost and availability, that would be an issue too. So like I said, for some of these where the only thing that matters is like the end result, like, maybe a little bit more finance or, something like that. I see it in its own workflow to help QML as we see it today, right? So it'd be an issue with a patient data, sensitive data, those types of things. If you're just especially inferencing one or a couple images, that would probably not be a good thing for medical at this point.
Yeah, just one more question before you move on. So, what do you think about quantum memory and storage, especially when it comes to encoding data? And how do you think the actual architectures are going to play out in terms of like actually sort of encoding and then inferencing, then coming back and iterating off that and trying to help sort of keep the integrity of the data, especially because of quantum decoherence?
Yeah, yeah, and the most recent things I've read with quantum data is basically you can go straight into a variational circuit without having to encode. Is that for the time being, and in say like the next years, we're mostly going to be dealing with classical data. So that means you have to encode it into quantum states. So I mean, outside of a few research labs where that's what they do, and there's a lifespan of the quantum RAM and those types of things, is that I don't see it's anytime soon, with quantum memory, quantum RAM.
Mm, okay. Yeah, that's it for now.
Yeah, anybody else?
Hi, Kevin. Can you go back to this slides which contains some pie chart?
You said pie.
Pie charts, some graphs, pictures.
Oh, pie chart. Okay, so
Yeah.
these.
Yeah, this one. I want to ask a question about QEA, referring to quantum evolutionary algorithms. It sounds like a buzzword. Can you explain that a little bit more? Because I read about some article talking about some specific algorithms like quantum Fourier transform, and then QAOA, something like that. Does that mean some specific algorithms?
Yeah. Yeah, and that's just it, is they're heavily researched. I mean, all three of those. And with QEA, especially from the beginning, it's something that appears from the literature, continues to get improved. So it does take, as far as, with this study, I tried to get, what happens quantum mechanically and what the results were for it. But, and according to this, and actually, if I look at you'll see a lot of QEAs going back in '02. So this Han and Kim. So, basically more Narayan and Han and Kim were kind of like the first founders for quantum algorithms. So you'll see QEA in 2002, and then it going, so 2011, more QEA. And yeah, it's like, according to that pie chart, it's pretty much one of the, if not the most studied quantum algorithm.
All right, got it.
Yeah, so it all comes down to, because there's a number of these papers that they claim you know, to get this performance benefit, but is there a loss in translation between, you know, people that actually understand quantum enough to use their own data to get that benefit from before? And, you know, that's just, it's inherent with any type of technology. You know, I think if you want customizability, you know, with a new data set, with a, you know, specific algorithms, is that you'll have to learn the technology. So quantum gates, you know, quantum circuits, which an algorithm is enclosed in it. And then now we're going all the way up to quantum machine learning. Any other questions? So this next part here, so these are all, so if you want to know how to run the right embedding and the right trainable gates, it's not that hard, but I think a lot of times you're given a certain algorithm template. So superpositioning, which is a Hadamard, some type of rotational gates, which is typically just one, and then a variational circuit, which typically includes entangling. But for classifications, and this is going off, this is one set here, is basically, this is a proposed algorithm search for this model. So this specific you know, the specific demo comes from Penny Lane, and it's from Thomas Bromley. And basically, you know, across many different types of architectures, this is what worked the best. You always want to do things experimentally, although some of the papers, they don't touch on it to get to that point. So to find the number of embedding gates is basically to use a certain number of rotational Y gates. So what that means is that the inputs, or the actual data itself, are the angles of the quantum gates. And that's what's changing, you know, the qubit as it passes through time, okay? And the next step is to start when you find the embedding. So say for this one, I try 1, 2, all the way up to 8, and at 8 rotational Y gates for the embedding worked the best, you know, gave the best results in this, in other cases too. And then try to add these rotational trainable gates, RYTs, up to, you know, to try to see if you can improve the performance. On this specific example, it's only needed to use embedding gates, right? So sometimes, and it may have to do with data set complexity, number classes, these types of things. But that's kind of what I experienced is with this specific one, just using an embedding. With this specific one, just using an embedding. And this is called the Convolutional Neural Networks demo by Penny Lane. This one is interesting because it's not deterministic. Every time you run it, you're going to get different results typically. So anyways, the prescription for this is to run a single RY embedding, and then, you know, multiple of these. So they're trainable RYs and CZ gates. So CZ is, you know, between two different qubits, like this would be 0 and 2. 0, 1, 2, yep. So anyways, what worked the best for this is just the embedding. And it's important to experiment. And that's the point of all this is like, yes, we have this fantastic literature and they were able to convert it from theory to implementation, but you'll have to run experiments, especially on your own data sets, to see what works best. And it's not always the case that entangling or even superpositioning sometimes is the best case to map data. So we're talking like, you know, more in the realm of quantum metric learning, which is done by MIT. And then in this one, it actually does help. So this is a 20 qubit circuit for quantum transfer learning on 10 class of brain tumor images. And I've used the HRY embedding before, and due to RAM restrictions at 16 gigs at the time, and now I have 51 gigs, I can add these trainable gates, and it helps, right? So you always want to see if the embedding's not right. So if you're just doing classifications, these 3 slides are definitely for you, because it's the practical application of what actually works, right? Say for instance, their recommendation puts you way over in RAM. What's the most important part to keep? You know, it's the embedding. So, and then, okay, so any questions? I saw there's a couple things in the chat here. And let's see. Yeah, so as far as all this stuff is, I like, again, if this is in person, okay, so this is Tanmoy. So I don't see anything coming close to being part of a workflow, in anything that we're talking about, quantum inspired, you know, these, quantum mechanics in machine learning. It's going to be a separate thing, I think, as far as fixing an algorithm related to QML workflow. So yeah, and it's a huge issue, right? So quantum noise will be, it's like many orders of magnitude off at this point. Any other questions? And the rest is supplementary, but it's really important. So, for people coming from different backgrounds, so say for the formal, this will probably make sense for you a little bit more. Now, the one that I'm most accustomed to is circuit, and then the bottom one is graphical. So this is basically, when we're talking about embeddings, state preparation, this is classical, data going into quantum states. The model circuit is typically some form of trainability or entangling gates, 2-qubit, 3-qubit entanglement gates. The measurement turns it back into binary for a qubit. So, and that goes back into, the regular workflow. And so there's a bunch more of these, and these kind of line it out because these are useful if you're looking for specific types in medical data sets that people use. So you see cancer, breast cancer, all different types of heart data set, cancer and MNIST, these types of things. So it's a very common thing to study quantum machine learning for medical purposes. And this is always good to have. So if you're just completely fresh out of it all, it all comes down to the qubit. Yes, this is 4 qubits here, which, in Qiskit or Penguin, we call it Q0, 1, 2, and 3, because it starts at 0. But ultimately, what's happening in an embedding is, that input data, if it's certain mini batch with that many images, is going in and it's changing the angle on that qubit. And then if you have trainable gates, and this is a qubit here, the trainable gates are actually more like machine learning gates, where the angles are adjusted over time to be most optimal. So the given state of Penny Lane and Qiskit, I don't see, especially for machine learning, I don't see it staying the same. I see innovations coming, and they had recognized that, maybe not using a gate model, which is more of what this is. But there's many ways of doing quantum mechanics, right? So it's, don't always think that just how you see it on the screen in these demos is the only way to do it. And this is basically a really important slide. So basically on the left are the quantum algorithms and the time complexities for it. So we see, they call it REC systems, supervised clustering, PCAs. And on the right are, going from worst to best, dequantized algorithms that don't necessarily have to have the same time complexity. But for instance, these are 4 dequantized algorithms that they don't have quantum mechanical information, but at that same time, like a AF over sigma is preferred, I believe, over this last one. So you would look at the quantum algorithm, and then you would look at the last one is typically how they rank it. So that's how they say the dequantized algorithms are presented loosely in order of decreasing time complexity, which would be, these are the best towards the right for dequantized. The current time gap, the current time complexity gap between the QML, which is this left one, and classical algorithms can be observed. So, that's basically what's being seen here. And then, so you'll also see practical application domains of QML, summary of works that report experimental results and their availability of the source code. Now, what's interesting about this, and this is going to the 2023 survey, the QML survey, is you'll see the dequantized algorithms. There's hardly any there. And I believe in this chart, it's basically saying, as far as time, what would be better to you, or what's comparable in these, because the previous one says there's different dequantized algorithms, but as far as time complexity, what it looks like between these two charts is it's still heavily favoring to keep the quantum information. This may change over time, right? So if there's new methods and these types of things. Now, if you strip things of the quantum information, that helps run things faster. But according to this author, it's very hard to do. And as you can see, there's some, but it's something to keep in mind is that this research can be used to get the best results quantumly, and then just try to dequantize it because there's some benefit if you can do that. But like I said, it's trickier. And then these last couple here is basically tensor networks, and people ask me like, how far off are they? I haven't seen anything personally that to me, besides people saying they're going to go up a huge number of qubits with them. And actually NVIDIA has taken it up to like thousands or more of qubits. Is that you see in this first part, it's actually the classical algorithm does the best. So ensemble, convolutional neural net, 99.91. And this bottom one, I think what it's showing is basically a similar type of thing. So basically, the classical is marked by the star. So yeah, I think the classical are favored for the MNIST and fashion MNIST as of later 2023. And if we go to this lower right with binaries, which is only 2 digits of 10 digits of MNIST, the quantum tensor network is preferred in this specific case. So I think it has more of like the method behind it, because I have seen demonstrations and they get down to the end, there's a talks or lectures, and they'll say like, well, what's the end result of this? And they say, well, we still haven't gotten that better performance. It is an approximate method, which means that, you might be losing some of that performance and if you're trying to do classifications. And then here's a table in this upper right-hand corner too that shows the amount of quantum mechanics integration. So dequantizes essentially zero, and it started off quantumly, and you strip it of quantum. But again, these are few and far between now, but it's something to keep an eye on in the future. So then tensor networks, and then you see quantum kernels, VQCs, which a lot of us probably here have run before. And I think that leads us, and benchmark functions. So, and again, I think this is for, I'll have to double check this one, but I think this is for benchmarking quantum algorithms or QML algorithms, these different techniques. Any questions at this point?
Yeah, so I wanted to ask, especially for scalability, what are the main issues for larger quantum networks? Of course, in terms of complexity, it will get really hard to manage it. So how's the research on managing complexity, especially for deep quantum neural nets?
Yeah, and I see it's both, right? It's software and hardware helping this. So one of these, okay, so I'll get you back up there. So basically, in these cases, I think here. So circuit cutting, mid-circuit measurement, qubit reuse, tensor networks, parallel neural networks. Now, the issue is if you want to run 100 qubits on any simulator, and especially if it's quantum machine learning, which has added complexities of probably a big data set and other classical algorithms, we're typically talking these days of doing a single circuit at like 30 qubits tops, because it gets exponential RAM even quicker in my experience than runtime. So that's the issue. And PennyLane did somebody asked about QAOA, quantum approximate optimization algorithm. PennyLane took, I think it's 129 qubit with circuit cutting on a supercomputer, and it's cutting it into pieces, getting individual solutions, and then putting it back into it, the final answer. So they were able to do that. So at 129 qubit, for that. But yeah, I think if you were to just, jot down all the things that you can do with quantum inspired machine learning, it's a lot. And I found myself, so 20% increase in loss efficiency if I switch to a double circuit in parallel as opposed to a single one. So that's a big bump because these other papers are saying like 15%, over classical algorithms. So yeah, it's these days it's going to be like that. You're going to have to find, the very specific things that'll help your use case. And, as we get more and more of the kind of like the things that definitely drive better results. Any other questions?
Yeah, actually, I have a question. So, are there any medical data like that is not solvable by classical machine learning algorithm, and that is only solvable by QML, and or from a data set, is there any parameter exists that I know before that what kind of algorithm I need to use, the quantum machine learning algorithm, or I need to use the classical machine learning algorithm to get better accuracy? So my question is more about the quantum advantage of quantum machine learning. I mean, is this thing explored, or are there any work on this in this direction?
Yeah, and I would, the best thing to do, like for all of us, is to keep reading the 2024 QML papers as they come out. And, there's trying to think, I've done these demos ad nauseum, like twice, if not more, on a specific demo from Qiskit and Penny Lane. And they're not huge models, right? They just aren't. So I think the answer to your question is this, is what would help the most is find the most efficient uses of quantum mechanics, i.e., is running like a full circuit the best way to go in this specific case? There's different ways of you could measure the learning the measurements from the outputs, of the quantum circuits, and just many different ways that you probably haven't thought of. But that's my approach, is basically, take all this information, keep reviewing it, and then moving forward, what's going to be the one that's not going to cost me as much in embedding, measurement, those types of things. I think it's a very specific question. I think it's a very specific answer, but it's based on what's been done before, so getting advantages with quantum algorithms, but now we're doing it with quantum machine learning. So it has to be applied correctly, I think, in order to get your consistent good results.
Yeah.
Any other questions? And there was another question here. So are there any medical data which is only being solved by QML, not classical ML? So it's basically every classical algorithm you can do with QML, but you can't do every traditional algorithm with ML, or you can't do every quantum algorithm with machine learning. So it's always the case that you can. It's just what you're weighing is basically the quantum benefit versus encoding the data, decoding the data, these types of things. And medical data, a lot of it's just very synonymous with any other types of, if it's an image and you have like 10 directories or 10 folders of images, you label each of those like glioma, meningioma, these are like brain tumors. And instead of like ants and bees, right? Like insects is how a demo might start out as. So I think from that question is basically I would do the quantum transfer learning demo to start off, if the Penny Lane one. The other ones is the torch. To go straight into neural networks, it has a scikit-learn data set in it. It's a basic one, but it allows you to do many experiments and draw these conclusions, which are probably pretty accurate. So I would check out that. It's like torch layers, Penny Lane torch layers. I would definitely check out. So these types of things will definitely, starting off with a demo, a good demo for you is good, but don't expect it to say that it's medical data when you can actually upload it with your Google Drive and you're pointing it to the correct directories and these types of things. If you have specific questions, like if you're going from binary to 50 classes, yes, you're going to have to change something in the notebook. Instead of it being 2, you changed it to 50. And then if you change like deep learning from like a ResNet 18 to 50, you're going to also have to change the elements from like a 512 to 2048. So, stuff like that, but I think you can get pretty far in the penny lane QML demos, I would say, and keep more in mind of like what it's doing and can you put medical data in it, not whether it says it's medical or not. So I don't, I think that's probably the best approach. Any other questions? Awesome. So if there's nothing else, I appreciate everybody coming on. This has been discussion 119, January 25th, 2024, for QML or effective QML algorithms for healthcare. I wish everybody a good rest of the night and a productive rest of the week. Take care, everybody. Bye.